So let's take a look at a damp spring oscillator. And let's see if we can analyze the forces, come up with a differential equation that will allow us to model what happens when we have a hanging spring that has mass on it, has a dampener on it, and is released and let to vibrate up and down. So you'll have videos that will allow you to see this behavior and collect data from it. Let's also see if we can model this situation so that we can compare what the model says to what actually happens. So let's suppose that we have something that we're hanging a spring from. So a lot of springs come in two forms. One is a compression spring, and that's a spring that you're simply pushing against. So it might normally be stretched out, and then you're strictly just pushing against it. And then some springs are tension springs. To begin with, they're not stretched at all, and we wouldn't really accomplish much if we pushed against it, but we can pull against those. So that's the type of spring that we're going to be dealing with. So let's suppose we hang a spring, a tension spring, and we don't hang anything from it and it's completely unstretched. So put a mark here for reference. And then let's compare that to, let's suppose we put some mass on it. So if we apply mass to it, then of course that's going to make it stretch. So here's our mass stretching out. So let's put a mass on there. And we're also going to have a damper on there. So I'm going to put a damper here on the bottom. Let's change the color of that. So if this is at rest, then the velocity is 0. And let's compare this point to this point. So this distance from where the end of the spring started to where the end of the spring now, I'm just going to refer to that as S. That's the stretch of the spring. For our project, we're going to denote this position as y equals 0. Now, after we get through some initial stuff, it could be that we technically measure y equals 0 from somewhere else, but at least for now, we're going to call the position at equilibrium y equals 0. We're going to refer to up as being the positive direction. So when our spring is at rest, then let's analyze the forces on it. We have the weight pulling down, which is the mass of this system times gravity, and we have the force of the spring pulling up. So if we sum those forces together in the y direction, that should equal mass times acceleration in the y. And if it's at equilibrium, if it's sitting still, then our acceleration is 0. So mass times 0 would be 0. So our force from our spring is up. Down, we have the weight, and those should add to 0. So if we move mg over, then the force of the spring is equivalent to the weight of our system. And how do you calculate the force on the spring? It's proportional to the stretch. So K times S equals mg. So as we went from here up to here, that's how much it stretched. So that stretch times some constant of proportionality, which we refer to as the spring constant, that's the force applied by the spring. And in this case, that equals the weight. They're equal and opposite forces. So what we're going to do is we're going to move our mass from equilibrium, either up or down, and then we're going to let it go. So if we pull it, raise it, or if we pull it down and let go, then it's going to oscillate up and down, up and down. So what I'm going to have you do is to raise it just a little bit. Instead of pulling it down, pick it up. So that'll get our spring or our mass up to here with our dampener on it. So if we're measuring from that connection point, then that distance is our current Y value. Now, if that's where we raise it to let it go, that's also going to be equivalent to our amplitude because that's the highest position it's going to be. So let's look at the forces that are acting on the box at this point. So we pushed it up. If we let it go, then its tendency is going to want to go downward, but it's not going to stop when it gets back down to here. It's going to continue going, and the spring is going to pull it back up, and it's going to oscillate up and down, up and down. So let's sum these forces in the y direction, and that should equal mass times acceleration in the y. So what are some forces we have? We have its weight. So we have m times g. And the weight is always towards the center of the earth. It's always downward. So if we call up positive, then that force is going to be negative. Another force we have is the spring force. So K times however much our stretch is. I'm just going to put a parenthesis there, and we'll come back to there. Actually, let's just do it this way to begin with. Let's call that the force of the spring. So we have the force of the spring, and the spring is always going to be pulling it up. At different times, it's going to be pulling at different amounts, but because whether we're here, whether we're here, whether we're here, that spring is stretched, then that force is going to be resisting that stretch, so that force is going to be up. The other force we have is due to the dampening force, in our case, air resistance. So as this oscillates up and down, air is going to be slowing it down. So that's proportional to its velocity. So let me be careful before I put a sign in there. So that's the dampening force. And when we add those together, that gives us mass times acceleration. So now the question is, well, which direction is the dampening force? If we're calling up to be positive, if the velocity, if it's moving in that direction, if we have a positive velocity, then the air is going to be pushing downward. The dampening force resists the direction that it's moving in. If it's moving downward, if we have a negative velocity, then the force is going to be pushing upward. So this force is going to be opposite of the velocity. So we could either call that plus b times the opposite of velocity or minus bv. So it opposes the direction of the velocity. So it's opposing that force. So let's go back and talk about the force from the spring. So when we lift the spring up, keep in mind that here at this point, our stretch is 0. And at equilibrium, our stretch is that amount. So if we move the block up, then the amount of stretch that's applied is this part here. So how can we achieve this value? So if this distance is s and this distance is y, if we take this distance away from the total, that will give us what we're left with. So that means this displacement is the total stretch minus the y value. So that puts it into reference to our coordinate system. So we have minus mg plus, so the force of the spring is k times the stretch, and we just said that the stretch is s minus y, then minus bv equals mass times acceleration in the y. So if we distribute to get rid of that parenthesis, we have minus mg plus k times s minus k times y minus bv equals mass times acceleration in the y direction. Notice that we said that ks is the same thing as mg. So if we replace ks with mg, those two are going to cancel. So then we'll be left with minus ky minus bv equals mass times acceleration. So our weight, even though our weight does play a role in the oscillation, because of the way our coordinate system is set up, the way that we're starting from equilibrium and then we're either pulling down or pushing up, then that already takes into consideration our weight when we look at what our starting point is. So velocity, that's the derivative of our position. So we have minus ky. Velocity is the first derivative of position. Acceleration is the second derivative of position. So we can get all of these on one side. So if we add these to the other side, we would get mass times y prime plus b y double prime plus b times y prime plus ky equals 0. Or you might rather call that mass times y double prime plus b y prime plus ky equals 0. So one good thing about this is that this is homogeneous. So we don't have to get a homogeneous and a particular solution. We can solve this and get the homogeneous solution, and that will give us the equation of motion for our damped oscillator.